Okay, today we are going to learn about mass spectroscopy or spectrometry, whatever you want to call it. This is another process that's going to help us determine the structure of a molecule. So what happens, and we'll look at that figure in a little bit, but what's actually happening is we send a molecule through a tube, and an ionized molecule through a tube, and it breaks up into fragments, okay? And we're going to get this graph from it, and it's going to tell us a lot about the structure. But what we're measuring based off is charge. We're measuring it off charge, and we're basing it off of mass, okay, as well. So we have a negative charge up here and a positive charge at bottom. So something that's positively charged, a cation is going to go closer. It's going to go closer to that negative charge. And if it has less of a positive charge, or if it's an anion, it's going to go in that direction. But for mass spectrometry, we only care about the cations. Another thing that's going to affect its path, if the molecule is larger, if it has a heavier mass, the momentum is going to carry it to the outside. And if it has a smaller mass, it's going to keep it on the inside. It's going to keep it on the inside. Okay, so those are two things you might get asked questions about, what the path looks like. Okay, so what happens after these molecules fly through that path? They hit this reader at the end that's going to shoot out a value on this graph on the right. So let's look at that. Okay, so the x-axis is very important. That's the m to z value, or mass over charge. And I'm going to put a positive charge for cation there, okay? Because one thing we need to know is that it has to have a cation, at least for the MCAT. It has to have a cation in order to be detected. If it doesn't have a cation, then it's not going to be detected. Okay, so we have this example here of strontium attached to a carbon and 3 hydrogens. It has its positive charge. So its mass comes out to 103. It comes out to 103, and its charge, its Z, would just be 1. So the signal it's going to produce is going to be at 103 over 1, or just 103. And we're going to call this the molecular ion. Now the molecular ion is what we measure when an electron is removed. So this compound, this molecule up top, had an electron removed. That's why it is a cation now, and the molecular ion is what it's officially called. Now we also have these spikes next to it. This spike right here at 104 would be called the M+1. This one would be called the M+1, or molecular ion +1, and then this one would be M+2. Now the +2, the +1 and the +2, those go to the mass. So it's going to be like 103 is the original mass +1 over Z, which is just 1. Okay. 1 cation, so I'm just going to write 1 actually, so just 1. Okay, so that's the M+1, so 103 plus 1 is obviously 104, and then the M+2 would be 103 plus 2 over the 1 cation. Okay, so we need to know this term molecular ion. We need to know that. The other term that we need to know, which would be this one, is called the base peak. We call it the base peak. What the heck is the base peak? The base peak is just the most abundant. The most abundant signal. That's it. That's all the base peak is. Now, let's say we didn't have this signal at 15 there. Let's say you removed that. The signal at 103 would be the molecular ion. It would also be the base peak. It would be both. Okay, so they can mix that up in the questions there. Just some stuff to pay attention to. So looking back and reflecting on everything, know the terms molecular ion, know the terms base peak, know how the molecular ion works, the math with it. So if they ever ask about the M+1, just know that it's +1 in the mass or +2 in the mass. It needs to be a cation in order for a signal to be produced. If there's no cation, you will not see a signal. And know how the pathway can be affected. Like, subscribe, and leave a comment down below.